Beginning with Thermo-Calc 2016A, TC-PRISMA, originally known as a standalone program, is now conveniently available as a precipitation module within the Thermo-Calc software package. This integration delivers a significant upgrade as it gives the precipitation calculator all the features that were already available within Thermo-Calc, expanding its functionality and eliminating the need for users to learn two programs. If you have Thermo-Calc 2016A or newer, simply click on the Precipitation Simulation template on the home screen of Thermo-Calc. When you do, all the task notes needed to complete a precipitation calculation will appear in the project pane. Now that the precipitation calculator is in Thermo-Calc, you can use the built-in database package feature so that a pair of compatible thermodynamic and kinetic databases load simultaneously when you start the software. Users can either access the default database package or define their own when you use Thermo-Calc 2015B or newer. This is convenient as you need both a thermodynamic and kinetic database to run a precipitation simulation. You can change which database or package loads by default upon startup by going to Tools, Options, Graphical Mode, Activities, and System Definition. You can select either a database or a package and which one you want. This integration also gives you easy access to the phases and phase constitutions, so you can configure phases and add composition sets if necessary. When you click on the Precipitation Calculation node, you access the newly integrated Precipitation Calculator and can see the brand new layout. The precipitation calculator was designed to be easy to use, so the default layout only shows the most common settings for matrix and precipitate phases. Users can easily access additional settings by clicking the Show Details buttons for each of the phases. You can easily change your default settings by going to Tools, Options, Graphical Mode, Activities, and Precipitation. Here you can customize the settings to make the program convenient for you. The integration into Thermo-Calc also means that users can take advantage of features such as cloning activities, which not only saves you time by reducing repetitive work, but it also ensures that your configurations are identical. This integration also gives you all of the plotting and tabulation features that are already available within Thermo-Calc, such as adding additional axes and overlaying plots. You can now quickly and easily look at many aspects of the calculation, such as mean radius, number density, nucleation rate, and more. Adding variables and replotting is fast and easy in this newly integrated module. In order to show you some of the new features available in this newly integrated precipitation calculator, I'll walk you through a basic precipitation calculation and highlight many of these exciting new features. I will use a binary system so that all users, including those who do not have a TC-PRISMA license or the necessary database package, can still complete the calculation using the free demo databases included in your software. This calculation is based on example number 13 of the examples that were included in your installation, so you can use the example file if you'd like to. We will do an isothermal precipitation calculation for the formation of aluminum-3 scandium in an aluminum-scandium alloy at 350 degrees. To begin, click on the Precipitation Simulation template to get all the nodes we need for the precipitation calculation. Set the database package to Demo, aluminum-based alloy. This will load both the thermodynamic and kinetic aluminum databases. Select the elements aluminum and scandium and set scandium to 0.18 mole%. Our system is now defined, but before we start the precipitation calculation, I'll do a quick step calculation to find the phases present around 350 degrees. Right-click on the system definer, highlight Create New Successor, and select Equilibrium Calculator. Set the temperature to 300 degrees Celsius, then select Property Diagram under the calculation type. We're looking for the phases present around 350 degrees, so set the range from 300 to 700 degrees to capture the temperature we want. Our system is now defined, so right-click on the Equilibrium Calculator node, highlight Create New Successor, and select Plot Renderer. Right-click on the Plot Renderer node and select Perform Now. Once the calculation is complete, a plot will appear in the results pane. We are looking for the phases around 350 degrees, so zoom in around this temperature to get a better view. We can see that there are two phases present at 350 degrees. FCC A1 makes up more than 99% of the system. The remaining part of the system is made up by aluminum-3 scandium, which is the precipitate phase in the alloy we're considering. Remember these two phases because we'll use them in our precipitation calculation. We're now done with our step calculation, so click on the Precipitation Calculator node to begin our precipitation calculation. Notice that our composition carried down from the system definer. Under Matrix Phase, select FCC A1. Note that if you do not see any phases listed here, it is probably because you do not have a kinetic database selected. If so, simply go back to the system definer and add a kinetic database. Next, we'll set our precipitate phase to aluminum-3 scandium because that is the other phase present around 350 degrees. We will accept the default settings of homogeneous nucleation in the bulk and interfacial energy estimated by the program. You could choose to define your own interfacial energy settings if you have them. Under Calculation Type, make sure Isothermal is selected, then set the temperature to 350 degrees, and set the time to 1e⁷, which is 10 million seconds. Finally, click on the Plot Renderer node and change the axis type to logarithmic 10 so we get a better view of the plot. Then click Perform at the bottom center of the program. Once the calculation is complete, your plot will appear in the results pane. This plot shows us the mean radius of the aluminum-3 scandium precipitate as a function of time. We can see that at the beginning, the mean radius is quite small and then grows rapidly over time. This new module makes it easy to look at a variety of variables. Simply click on the Axis Variable tab to see what is available. I'll select number density. This calculator also allows you to add additional variables to the same plot so you can compare the results. Simply click the green plus sign to add a variable. Let's select nucleation rate, then click Perform again. This new version of the precipitation calculator makes it quick and easy to make changes and replot results, so your plot should reappear almost instantly. Our plot now has two y-axes, one for each variable. We can see that nucleation makes the number of particles increase. At a later time, we reach the coarsening stage where the smallest particles shrink and the total number of particles decreases. The integrated precipitation calculator also makes it easy to add additional plots. Simply right-click on the precipitation calculator, highlight Create New Successor, and select Plot Renderer. Let's look at size distribution this time. Notice that final simulation time, 1e⁷, auto-populates. It's also easy to show the size distribution for several times. Simply enter the times in the time field and separate them with either a space or a comma. I'll enter 5, 10, 100, 1000, and 100,000, and I'll leave 1e⁷. Change the axis type to logarithmic 10 again, then click Perform. All the size distributions show us that as nucleation is occurring, the size distribution grows. But when we reach coarsening, the height of the size distribution decreases. Finally, if you're using the example file to run this calculation, you'll see the experimental results in the plot. We can see that they have fairly good agreement to our calculation, but it is not perfect. This can be improved by changing the interfacial energy rate. The newly integrated precipitation calculator makes it easy for us to do this through cloning, which allows us to keep our first simulation and create an identical copy that we can make changes to and compare to the original. Right-click on the precipitation calculator node and select Clone. You can also clone the entire tree, but we only need one node, which will connect to the existing plot renderer to compare the two sets of results. I'll change the name of this new calculator so that we don't confuse the two. To do this, right-click on the calculator, select Rename, then rename it to Sigma Prefecture 0.8. Then click OK. Now change the interfacial energy to a prefecture of 0.8. Next, we need to link the plot renderer to the second calculator so that we can directly compare the two. Right-click on the plot renderer node, highlight Add Predecessor, and select Sigma Prefecture 0.8. Notice that the plot renderer is now linked to both precipitation calculators. Make sure that the axis type is set to logarithmic 10 under both axes. Then select the tab for the second calculator and change the axis type to logarithmic 10 under both axes there as well. Then select Perform. Once the plot is updated, we can see that the average radius is similar in both calculations, but there's better agreement with the experimental results at a prefecture of 0.8. We hope you enjoy the newly integrated Precipitation Calculator module, also known as TC-PRISMA. We will be working on additional examples videos in the near future, so check back regularly at www.thermocalc.com.